Okay, so now, first the cardinality of H is the same as the cardinality of any coset. If you pick a particular G in G, I don't know, then you can define a map from H to GH by, I don't know, taking H prime and H. That's going to go to GH prime for GH. That's our map. So the question is this map 1-to-1 and onto so that the cardinalities are equal for H and GH? Well, first for onto, for any element in GH, for a particular G, the way we make this map, so I mean GH prime, if it's an element, that came from H prime and H. You just multiply that element by G to get to it. So it's onto, by the way, it's by definition, this is the way you make a coset. You multiply everything in H by an element of G, and that makes the coset. So this map from H to its coset is onto. Now for 1-to-1, if you take an element in here like GH1 and an element GH2, if they're equal, multiplying the left by G inverse, that'll give you H1 equals H2. So in other words, the map, individual elements of H1 go to individual elements G of H go to individual elements here. So this, if each H goes to unique GH. If two of the H's go to the same element in here, they're equal, then they came from the same element in H. Okay, so 1-to-1 and onto. So the cardinality, all the G's, all the cosets have the same number of elements because we just showed that map. So that's important to remember. Every coset has the same number of elements. Now, we showed in the previous that the union of the cosets equals G. So we know all of G is in the cosets. So now we need to show that if I have two cosets like G1H and G2H, that their intersection is non-empty. So we take the intersection of G1H and G2H. All right, so suppose X is an element of this. Suppose the intersection is non-empty. I need to show that this and this, if they overlap, they're actually the same set. Like the whole set matches. So what I want to do is show that if Y is in G1H, then it's in G2H. I'm going to show containment in each direction and show that G1H equals G2H. Okay? So I'm going to show that this being non-empty implies these two are the same set. So X has got to be, if it's in G1H, it has the form G1H1. But if it's in G2H, then X has the form G2H2. Now I'm going to show G1H is a subset of G2H. If Y is an element of G1H, then Y has the form G1H1. Now G1 equals G2H2 H1 inverse. Multiply both sides by H1 inverse. So this G1 I can replace by G1H2, G2H2, and then multiplying the right by h1 inverse. So this y, which is g1h1, is g2. What is this? This is an element of h. So h2 h1 inverse, because inverses are in h and multiplication is closed in h, h2 h1 inverse is in h. So this g1h1 is an element of g2h, which is what I needed to show going to from the left to the right, that y must be an element of g2h. Do exactly this same thing in the other direction, but solve the other way. And you will get that g2h is a subset of g1h, so that they have to be equal if they're non-empty. Well, if they're equal, then the cosets are distinct, which means we have a partition. Technically, we have an equivalence relation defined by x is related to y if x is in the same partition as y. But now you have the cosets, and then you have a certain number of cosets. Each of the cosets has the number of elements that are the same in each coset. So, G1H, G2H, ... The group is the union of these we showed in the previous video. And we showed that these are disjoint. They don't overlap. So the union of these together make the group G. So that you multiply the number of elements by the number of partitions, and that's going to give you the order of G. And that's Lagrange's theorem. That's one proof. I have a few minutes, so let me give you another proof. So I want to show that this makes an equivalence relation on G. So if so the equivalence relation, x is related to y if x is in yh, is in the coset. So the equivalence relation is going to be in the coset of. So related to y. So let's see. Is x related to x? X is so x is in some coset G1H. And the question is x related to x? So if x is in G1H, x equals G1H1. Oh, well, if x is in this coset, then multiplying the right by H1 inverse. I got confused for a minute. Sorry about that. X is related to x because if x is in the coset, I guess I want to show that x is in xh for some h. So we want to show that x equals, x is, equal to the x times e. How much time do I have? So if x is in G1H, we need to show that x is in XH. That will show x is related to x. Oh, no, I don't start with that. The is relation to is x related to x is x in XH. And E is in H, so x equals x times E. So x equals x times E, which is x. So x is in XH. So x is related to x. That's what I need to say. Okay, so that's, what is it called? Symmetry. All right, if x is related to y, is y related to x? So x related to y means x is in YH. Well, that means x equals YH1 for some H1 and H. But then multiplying the right by H1, x H1 inverse equals y. And y is an element of XH. So y is related to x because H1 inverse is in H. H is closed under inverses because it's a subgroup. That's where we use that. So we get y is related to x. And then the last one is if x is related to y and y is related to z. X is in the y coset. Y is in the z coset. So x is equal to YH1 and y is equal to ZH2, let's say. Well, so y equals XH1 inverse equals ZH2. And then multiplying the right by H1, and that gives x is related to z. Multiplied by H1. So that proves x is related to z. So if you have an equivalence relation, you know the partitions are disjoint. It's not hard to prove. So that's another way that you get the partitions being separate on cosets. And we showed earlier that they have the same number of elements. So the product of the number of elements by the number of cosets, giving a partition on G, gives us the number of elements in G again. So I hope, I messed up a little bit in there, but I hope that makes Lagrange's theorem pretty clear to you. Thank you.